Hey there, curious minds, and welcome back to the Deep Dive. Today we're plunging headfirst into a truly electrifying topic, and I mean that literally. We're talking about supercapacitors. Those incredible energy storage devices that promise to charge way faster and last significantly longer than the batteries we're used to. But for years, there's been this persistent enigma right at the heart of their performance, the nanoporous carbon electrodes. For what feels like ages in the scientific world, the main idea, the design principle everyone was chasing, was pretty much all about pore size. The thinking was, straightforward, get those tiny pores just right, match them perfectly to the ions, and boom, better capacitance. Seemed logical.
It did seem logical, yeah. That was certainly the conventional wisdom. But as often happens in science, the reality turned out to be a lot more complicated. The research started getting, well, contradictory. Some early studies seemed to back up this pore size idea, but then later work just painted a much more muddled picture, which basically left researchers without really clear design rules. We're sort of flying blind, trying to make better supercapacitors. So our deep dive today is into this really groundbreaking paper by Xinyu Liu and colleagues out of Science. And it doesn't just offer an explanation, it fundamentally rewrites how we understand these things. It's kind of like discovering that the strength of, say, a building isn't just about how big the bricks are, but about how cleverly, maybe even how imperfectly, they're all put together.
That's a great analogy, a building's strength, from the way it's assembled, not just the parts. So if the old ideas about pore size were getting so fuzzy, how did these researchers start to, unpack this, find those hidden factors? What was the secret ingredient they were looking for? The thing that might change everything from our phones to electric cars. Okay, let's set the stage a bit more. We're mostly talking about electrochemical double-layer capacitors, EDLCs. That's a specific type of supercapacitor. And they're really valued for delivering power quickly and lasting for tons of charge cycles compared to batteries. The most common ones, the cheapest ones, use activated carbon electrodes. And you can picture these as these really complex networks of graphene-like sheets. But they're not perfect sheets. They're usually pretty disordered, full of all sorts of different sized pores.
Right. And the big goal, always, has been boosting their energy density. We want them to hold more charge, get closer to what batteries can do, but keep that speed and long life. And for decades, the main approach, like you said, was tuning that pore size, usually measured using gas sorption. Early work, especially on materials called titanium carbide-derived carbons, or TIC-CDCs, really seemed to point to the sweet spot. Optimal capacitance when pores match the desolvated ion size. That's around 0.7 nanometers. For a while, it honestly looked like a clear relationship, a simple rule for design. But then things took an unexpected turn. More research came out and it just got messy. Studies started showing this baffling lack of correlation between how well they stored charge and the size of the pores. And this was across a whole range of different carbon materials. It wasn't just a small thing either. It really challenged the core idea. For instance, one big study looked at, I think, 22 microporous and 6 mesoporous carbons, pores from zero point 0.7 all the way up to 15 nanometers. Huge range. And the finding, no clear link at all.
Other studies found similar things.
Very little connection, maybe only a tiny improvement, even suggested by complex computer models. So the field was kind of stuck. No clear path forward for designing better materials. It really strongly suggested there was something else going on, some other structural variable they hadn't accounted for, something fundamental.
Okay, so the established rules are kind of falling apart, leaving researchers a bit puzzled. How do you even start looking for this unknown structural variable inside this incredibly tiny, complex maze of carbon? It sounds like finding a needle in a haystack, but at the atomic level. So this paper introduces a technique that's elegant and powerful for seeing this.
Absolutely. The team turned to something called solid-state nuclear magnetic resonance spectroscopy, NMR. Now, you might know NMR from medical scans, right, like MRI, seeing inside the body. Well, solid-state NMR does something similar, but for materials. It's like this incredibly sophisticated scanner that lets us look at the local chemical structure. And crucially, it lets us see how charge is actually stored and distributed right down at the atomic level in these electrodes. It's really a marvel of physics, letting us peek into that quantum world. And their specific insight was to focus on something called the ring current effect. Okay, imagine the carbon atoms form these hexagonal rings, like little bits of graphene. When ions squeeze into the pores, the electrons in these rings, the pi electrons, they start circulating because of the NMR's magnetic field. This circulation creates its own tiny magnetic field, and that causes a distinct shift in the NMR signal we detect. The shift, they quantify it precisely as the A value, and that value becomes the key indicator, the molecular fingerprint, if you like.
Right, the O value. So it puts a number on something that sounds kind of abstract, like structural disorder. It measures how messy the carbon structure is. That sounds incredibly useful. Can you explain a bit more what these ordered domains are and why their size matters for capacitance?
Exactly. That low value directly measures how strong that ring current effect is. And what it's linked to, fundamentally, is the ordered domain size.
Hmm.
Think of it as the average size of the relatively neat graphene-like patches that make up the pore walls. If the carbon is like a patchwork quilt, the ordered domains are the large, regular patches. The disordered areas are where the patches are small, broken up, irregular. So a smaller magnitude value means smaller ordered domains. And that, crucially, means more structural disorder. It gives us this beautifully precise quantitative handle on molecular chaos, basically.
Which is vital, right? It moves us beyond just descriptions into hard numbers. Okay, so armed with this precise tool, they didn't just theorize. They went out and gathered hard quantitative data to challenge that old pore size thinking. They started with, what, 10 different commercial nanoporous carbons, the kind actually used out there.
That's right, 10 widely available carbons from different suppliers. First step, analyze the standard gas sorption data, porosity, surface area, the usual stuff. And what they found was pretty striking. 5 of these carbons had very, very similar pore size distributions. And similar bet surface areas, too, all around 1,700 to 1,800 square meters per gram. So, based on the old thinking, you'd expect them to perform pretty much the same.
Makes sense. Similar structures, similar results.
Nope. Despite that similarity in pores, their capacitance values were wildly different, from a high of 138 farads per gram way down to 83.
Wow, that's almost a 60% difference.
Exactly. A huge variance. Even though the porosity, the factor everyone focused on, was basically the same, that right there was a massive red flag. Something else had to be dominant. And to really hammer this home, they looked at 3 activated carbon clocks, ACCs. These actually had very different pore structures and surface areas. So here, the old idea would predict very different capacitances.
Right, different structures, different results.
But again, the opposite happened. Despite the clear differences in pores, these ACCs showed similar capacitance values, all clustered tightly together within about 9 farads per gram.
That's counterintuitive if you're only thinking about pores anyway.
Totally counterintuitive based on the old model.
So looking at the bigger picture then, across all their samples, including ones they deliberately heated up, annealed, you called it.
Yeah, we'll get more into annealing shortly, but yes, across all samples.
They found basically no obvious correlation between capacitance and the average pore size, just like a random scatter plot.
Pretty much, yeah. Just a scatter, no trend. Same for bet surface area, no clear link there either. They even checked things like oxygen content with XPS. Still no clear connection to capacitance. The message from the data was loud and clear. That long-held belief that pore size is king. Quantitatively, comprehensively challenged. It's just not the main story.
Okay, so if pore size is dethroned, the spotlight swings firmly onto this structural disorder idea.
Exactly. This is the real breakthrough. Using their NMR method, measuring that O value, the disorder indicator, they found this incredibly strong, consistent correlation between capacitance and border. It's laid out really clearly in their figure 2b, and the pattern was unmistakable. Carbons with smaller magnitude values, remember, that means more disorder, smaller graphene bits, those consistently showed higher capacitances. And this wasn't just in one type of carbon. It held true across materials from 6 different suppliers, even with different electrolytes. It points at something really fundamental, really universal about these materials.
Okay, strong correlation. But as they say, correlation isn't causation. How did they actually prove disorder was the cause of the higher capacitance, not just something that happened to go along with it?
Right, that's the critical next step. And their experiment was quite elegant. Thermal annealing. Think of it like taking the carbon and gently baking it at high temperatures. What this does, in a controlled way, is encourage the carbon atoms to rearrange into more ordered structures, like smoothing out the wrinkles. So they took 2 specific carbons, ACSPC, which was very disordered and had high capacitance, and EL104, a more ordered one. They annealed them at increasing temperatures, and their NMR measurements confirmed it. The A values increased, meaning the structure got more ordered.
Okay, so they're dialing up the order.
Exactly. And what happened to the capacitance? It clearly decreased as the disorder decreased, a direct inverse relationship.
So increasing order caused capacitance to drop.
Precisely. And crucially, They checked the pores again, using gas sorption after annealing. The pore sizes hadn't really changed much, so they isolated the effect. It wasn't the pores changing, it was the disorder level changing. And that directly impacted capacitance. It's a controlled demonstration. Cause and effect, like turning an order knob up and watching the capacitance dial down.
That feels like the smoking gun right there. Deliberately reducing disorder reduces capacitance. Did they back this up with other methods too?
We did, yeah. They didn't stop there. They used lattice simulations, computer models, to predict the size of these ordered domains. And those simulations lined up perfectly. Carbons calculated to have smaller ordered domains generally had higher capacitances, matching the NMR results.
Okay, so theory matches experiment.
And then for yet another angle, they used X-ray pair distribution function analysis, PDF. This technique basically maps out how atoms are arranged relative to each other. And the PDF patterns showed that the high capacitance disordered carbons, like SC1800, had atomic correlations that faded out much quicker over distance. That's exactly what you'd expect for smaller, more disordered domains compared to the more ordered low capacitance ones like PW400.
Wow. So NMR, annealing, simulations, X-ray PDF, they all point to the same conclusion. Disorder is key.
It's a really unified body of evidence.
And this lets us go back and understand those old, confusing results, right?
Yeah.
Like those tucky CDC materials made at low temperatures that had unexpectedly high capacitance.
Exactly. That anomaly reported years ago, shown in their Figure 2D, now makes perfect sense. Those low-temperature synthesis conditions likely produced more disordered structures, hence higher capacitance. It resolves decades of contradictory data. It's a real aha moment for the field.
Okay, so we've established that disorder boosts capacitance, with solid proof. Now let's dive into the why. What's actually happening down at the molecular level inside these messy carbon structures that makes them better at storing charge? This is where it gets really interesting, physics-wise.
Right. So to figure out the why, the team used ex situ MAS NMR, magic angle spinning NMR. They looked at electrodes after they'd been charged. They compared an ordered carbon, PW400, with a disordered one, SC1800, while they were holding charge. And they meticulously measured how many positive ions and negative ions from the electrolyte were actually inside the pores at different voltages. It's shown in their Figure 3A. Now, both types of carbon store charge using what's called an ion exchange mechanism. Basically, when you charge it, ions with the opposite charge to the electrode conterions go into the pores, and ions with the same charge, co-ions, get pushed out. It's a swap to balance the charge.
Okay, standard mechanism.
Yeah, that part's known. But the key finding, connecting back to disorder, was that the more disordered carbon, SC1800, showed a significantly greater ability to actually store ions at any given voltage compared to the ordered PW400. You can see that difference clearly in Figure 3B.
So the disordered one just holds more ions. Why? What makes it better at grabbing and holding them?
This is where the proposed physics gets really cool. The idea is that in these carbons with smaller, more disordered domains, the electronic charge on the carbon itself becomes more localized. Think of it like this. On a big, smooth, ordered graphene sheet, the charge might be spread out thinly, but in a disordered structure with lots of small bits and pieces, the charge gets concentrated in certain spots, little hot spots of charge.
Okay, like charge puddles instead of a thin film.
Exactly. And these localized charge concentrations create much stronger interactions with the ions in the electrolyte. They act like stronger anchor points, stronger magnets, pulling ions in and holding them more effectively. So you fundamentally enable more efficient storage of those ions just because the charge on the carbon surface is distributed differently, more localized, more intense in spots.
So the messiness creates stronger binding sites for the ions.
Precisely, and it might be even more specific than just general localization. They also suggest that these smaller disordered domains probably have a higher concentration of topological defects. These aren't like flaws you want to avoid. Here, they're potentially beneficial features, things like the edges of the graphene fragments, or maybe unusual rings like pentagons or heptagons mixed in with the normal hexagons, or even just points of high curvature. These defects create unique electronic and physical environments. There's previous work suggesting these kinds of sites can boost capacitance, maybe by allowing ions to pack more densely or by changing the electronic properties right at those defect points to make ion adsorption more favorable.
So the imperfections are actually enhancing the performance.
It seems so. It's a fundamental insight. The atomic level messiness, the defects, they aren't bugs. They're features that translate directly into better macroscopic energy storage.
What an incredible scientific story. Really digging deep with advanced tools like NMR and PDF to completely flip a long-held assumption on its head. It's not just about the size of the holes, it's about the actual fabric, the disorder, the inherent molecular chaos of the carbon itself.
Exactly. And this isn't just, an interesting academic finding. It provides really clear, actionable design principles for the first time, really. By understanding this and actually exploiting structural disorder, designing for it, instead of trying to eliminate it, we can now aim to create electrode materials for EDLCs that are much more energy dense. This means supercapacitors holding significantly more charge, bringing them closer to batteries in terms of energy, but keeping that amazing power and lifetime.
And for you, the learner, thinking about the real-world impact, this could translate into electric vehicles that charge much faster, maybe more efficient storage, for the power grid to better handle renewables like solar and wind. Or even just better performance and longer life from the portable electronics we use every day. It's a fantastic example of how asking fundamental questions and really following the data can lead to surprising and potentially transformative answers.
Indeed it is. So maybe as you look at the complex world, think about this. Could things we often see as imperfections or disorder, whether in materials or maybe even other systems, could they actually be the hidden key to unlocking unexpected power or functionality? This work makes you wonder, what other disorders out there might hold secrets for our future technologies?
That's a really fascinating thought to leave us with. What power lies in the imperfections? Until next time, keep digging, keep learning, and stay curious.